Hey there, awesome physics students. I wanted to take a second to talk about some of the units used to describe pressure. Understanding these units and where they come from is useful, especially for inferring whether you're given a gauge pressure or an absolute pressure. So let's go ahead and get started. The idea with all these pressure units is that we're in a sea of air and we have the weight of the air pushing down on us in every direction. And so there's this constant atmospheric pressure that is exerted on us at the bottom. And so we can talk about the atmospheric pressure and compare all of those values in these different units. In normal SI units, the one atmospheric pressure is normally defined as 101,325 pascals, and that's newtons per meter squared. Of course, we can also talk about how many atmospheres, like is it 2 atmospheres of pressure, is it 3 atmospheres of pressure, and so it's not natural to invent a unit called the atmosphere, which is 1 atmosphere is 101,325 pascals. Of course, then once you invent this, then a very clever person thought, hey, you know, if I just move the decimal place 5 times, then that will give me a number. So let me just move the decimal place 5 times, and that gives me 1.01325. That's almost equal to 1, but it still retains the proper number of digits, and converting to pascals is very easy. So that was created. That's called bar. Although I haven't seen it used too frequently except for in automotive terms. These units, unfortunately, are somewhat separated from the way it was traditional in the not too distant past to measure pressure. And so how do they actually measure pressure? Well, to measure pressure, one way to do it is to take a pool and fill it with a fluid, and then take a test tube, a very long test tube, of course, and fill it completely with the fluid and then put it upside down. So you have this test tube like this coming out, and the fluid is here. This is the level of the fluid. And because the air is pushing down all around on the surface of this fluid, that's 1 atmosphere of pressure is pushing down on the surface, the fluid will be pushed up into this tube and will fill this tube up to a certain point. And so the fluid will come up to that height, and of course this is just one continuous piece of fluid all through here. Now at the very top here at the fingertip of this is nothing. It's a vacuum. And so what that means is that there's remember, pressure originates from collisions at the surface of an interface, and since it's a vacuum up here, there's no atoms to push down on this. So the pressure here at the top is 0 in absolute terms. And so the pressure increases with depth here, and so you can use this depth to tell you how much the pressure has increased down to 1 atmosphere, right? Because the pressure here is going to be 1 atmosphere. If you do this with a variety of fluids, you'll get a variety of heights. It's convenient to do this with a very dense fluid so that you don't have to have a super tall column here. And so people would often use mercury. And if you do it with mercury, you'll find that it will push it to a height of 760 millimeters. So you can use the expression, the delta P is equal to rho, the density of the fluid, times g, the gravitational constant, times h, the height, in this case 760 millimeters, or 0.76 meters. And you can compute this number, but people actually found it more convenient to just put markings on the tube here and see how much it pushed the fluid up or down, and just read off the number, the height of the fluid. If you do this on average for the atmosphere, this will be about 760 millimeters of mercury. Now, unfortunately, this height is, or this unit is tied to the density of mercury. So if we refine the density of mercury a little bit more, then this number will change. It'll change out to, you know, 3rd decimal place or something like that. But it'll still change. We don't like that. So what people had done is they defined a new unit that is independent of the, it's not tied to the density of mercury, and it's called a torr, named after Torricelli. And that one is independent of the density of mercury. Now some people, they don't like millimeters, they don't like metric. Instead they want things in inches. And so if you measure this, just convert this height into inches, you get 29 0.92 inches. And so you can also talk about it in terms of inches of mercury. And sometimes you'll see this on the weather forecast. They'll just give you the pressure in inches, and they will drop the Hg, the mercury part. Okay, so that's nice and convenient. And now there's one more that you may have been familiar with if you pumped your bicycle up with air or a soccer ball or a car tire, and that's PSI. So 1 atmosphere is about 14.696 PSI, but PSI stands for pounds per square inch. So this is actually a pound per inches squared. So this is a force over an area unit, just like a Newton per meter squared. But we don't use that typically here. So anyway, it's good to know what these are. That way, if you're given a unit, you can figure out whether it's about equal to atmospheric pressure or not. Incidentally, it's useful to know that blood pressure is given in millimeters of mercury often. So that's another useful tidbit. As a challenge to you, I would see why don't we use water? Water is so much more convenient than getting mercury, and it's less toxic too. So why don't we use water to do this? So what you should do is compute this rho GH for water and see how tall would the tube need to be if you measure this with water.